Today we're going to study the photoelectric effect. So if we take some piece of metal, okay, so this is a piece of metal. I put here metal. Okay, this piece of metal has electrons, protons, neutrons, but the electrons, because the metal has so many electrons, and since the atoms are packed next to each other, some electrons are actually free to move between the atoms, because those electrons that are free to move, they get screened by other electrons, and the nucleus of the atom cannot see them as well or exert on them the force of attraction as well, so they kind of roam around on the metal. So if a photon or a bundle of energy of light coming in, here is the photon coming in with certain energy, let's see, from the sun. Here is the sun. So the energy is coming in from the photon. This energy of the photon is equal to Planck constant times the frequency of that ray, the frequency. Now this Planck constant H is very small, is equal to 6.63 times 10 to minus 34 joule second. Now this is the energy of the photon coming in. The electron here, they're moving about, randomly going around. So if the photon has enough energy to hit the electron, let's see, the electron is here somewhere. The photon will hit it. The electron will jump. If the energy is high enough to allow this electron to jump, then it will jump. Now, these electrons, some of them, like I said, are free because of the screening, and some of them are attached to the atom through binding energy. There is a binding energy between the electron and the nucleus or the atoms, and that energy is the one that's holding the electron from leaving the atom. So some physicists, they call it the work function. Some physicists, for simplicity, they just call it the binding energy. So if this energy of light is high enough, so it will give the energy to electron, it will satisfy the binding energy. The atom will lose the electron because the energy that's coming from light is high compared to the binding energy. So the electron will leave like that, will jump. So we can write down an equation. So we can say the energy of a photon, so I put here E gamma, we just call it energy of photon, minus the binding energy, they call it the work function phi, this is the binding energy, is equal to what's left, which is the kinetic energy. And here I put the mass of the electron. So if this energy is high enough, then the electron will dissociate from the atom and will leave the metal. Now what happened is we need to change this equation to show that this energy here, let me put here H, this is Planck constant, this is F, the frequency of light, and minus the binding energy is equal to 1/2 MeV squared. So here is the equation for the photoelectric effect. So if you know the binding energy and you know the frequency of that light that's coming in, you will know the velocity of the electron leaving the metal. Now, let's see if the velocity is zero, which means the electron gets dissociated from the atom, but it doesn't go with the velocity, it just sits there. Here is the metal, okay? Here is the electron, it's not moving, it's just sitting there. It's free now from the atom, but it's sitting there. So in that situation, I just put the electron sitting. Now, this electron doesn't have velocity, so the equation changes. So we put here h times the frequency minus phi is equal to 0. So I put here velocity is 0, electron is not moving. It's not moving. Now, the work function or the binding energy is equal to, I put here HF, and I put here critical. So there is this critical frequency of light that tells you about the binding energy of that electron to the atom. Let me box this too. So this photoelectric effect is actually very useful in technology, because if you take this is some panel, for example, okay, and then you expose it to the radiation coming from the sun. So here is the radiation coming from the sun. Now, if this radiation hits the metal, the electrons will become free. You actually free the electron from the metal. And then you have these electrons. And then if you give them some difference of potential, like you put here this side you make it positive, this side make it negative, then this electron will move. We move with some drift velocity, and then you generate a current. So this photoelectric effect can be responsible in explaining the solar panel current, and is very useful in technology. So one thing you need to know is this thing that I call the work function. I put here phi work function, or phi binding energy. Is the same thing. Okay. So this phenomenon that I just explained is called the photoelectric effect. Now, you can make the equation, you can change it a little bit. We know that lambda, this is the wavelength, is equal to c over the frequency. So the frequency f is equal to c over lambda. Now, I can change this equation here into this. I put h, okay? I put h, and then instead of putting f, I put c over lambda. C over lambda minus the binding energy is equal to 1/2 me v squared. This equation tells you about the wavelength of that light that came in and hit the electron. So you can either use this equation or you can use this one. Okay?